Okay, so sorry for the long delay here, but we're going to talk about the ionization of acids and bases. And one of the first people that was looking at what acids and bases are was Mr. Arrhenius, Svante Arrhenius. And I can imagine that he was also involved with or since he was involved with the explanation of the conductivity of solutions, that maybe what he was doing one day was he got tired of testing salts and other covalent compounds, and he strayed into the acid-base aisle and dropped his conductivity apparatus into these solutions to test them out. So for instance, if he made an aqueous solution of sodium hydroxide, that looks a lot like, sodium chloride. We're familiar with the sodium ion and hydroxide ion, so I might expect, because sodium is one of my always ions, that this would be completely soluble in solution and break apart into ions and conduct. So let's just see what's going on. So he flipped the switch, built up some charge, and lo and behold, the solution conducted electricity. And what he speculated was that bases are substances that ionize to produce hydroxide ions. So we can show that through the direct ionization of sodium hydroxide into its component ions, sodium and hydroxide. So now let's take a look at acids. So I've got an acid here, HCl, and maybe at first glance, what Mr. Arrhenius thought was maybe this isn't going to conduct electricity because both hydrogen and chlorine are nonmetals. So I've got what amounts to a covalent compound. So I'm not expecting that to conduct electricity. But as he flipped the switch and turned it on and let it go, it lit up. So he had to kind of scratch his head a moment and kind of go, what the? So if it's conducting electricity, there must be ions present, and since there are only two atoms involved in this compound, these must be breaking apart to form ions. So what Svante Arrhenius said was that acids ionize to produce H plus ions, or hydrogen ions. So one of the initial theories of acids and bases were acids produce hydrogen ion, and that bases produce hydroxide ion by direct ionization. And you might have noticed that the acid and base that we use, sodium hydroxide, ended with OH. So if you see a formula that ends in OH, it's very likely a base. And if it starts with an H, it's most likely an acid. Okay, so there's the ionization. Let's get on with this. So there were a couple other deep thinkers in the acid-base world. They looked like very stern fellows, Mr. Bronsted and Mr. Lowry, and they had some thoughts of their own, and they said, well, NaOH, it ends in OH, and it's a base, but we've been dipping litmus paper into solutions while you've been testing them for conductivity, and ammonia tests as a base, and we don't see any stinking hydroxide in the formula. So what's going on here? So we had to come up with an alternate theory, and what they have here is basically that ammonia is accepting a hydrogen from water and producing ammonium ion, but when that water gives up that hydrogen, what's left over is just the hydroxide ion. So I've got kind of a Lewis structure picture here. So one thing about nitrogen is it's got a fat, juicy pair of electrons, and hydrogen is in a very unequal relationship there with oxygen, and it has, maybe 25% of those electrons between them, and they can see that they can get a better deal if they float off and join up with those pair of electrons on the ammonia. So, like that. And that hydrogen ion lands on the ammonia. So they came up with theory that bases are hydrogen ion acceptors, and probably the most likely donor in just aqueous solution is going to be water itself. They also had some observations about acids, and I can imagine that maybe they said something like, "Yo, Svante, we don't think that H plus ion that you have in your acids would actually exist in solution." If you really think about it, when you strip a hydrogen atom of its electron, it often is compared to that the nucleus is like a tiny baseball in the center of a large baseball stadium, and the electron is, circulating around that in a space the size of the entire stadium. So you've got a very tiny concentrated positive charge floating around in solution, and it's very likely that that would be something that the negative end of a water molecule would be very attracted to. So they also proposed a theory of acids or acids as well as bases, that that hydrogen ion would actually be donated to water to form hydronium ion. So that H3O plus is known as the hydronium ion. So the hydrogen on the HCl is donated to water, and we end up with hydronium, and that hydrogen is now sitting on that formerly water molecule, and we call that H3O plus. We call that hydronium. So their theory was that acids are hydrogen ion donors. Okay, one thing to get out here is we have some acids and bases that we all agree are strong, or at least many people agree, and I think these were the ones that were in our textbook. So you don't need to memorize these. If you memorize a couple of them by accident, that's great, but they will be included on the test. So if it's a strong acid, that means that it ionizes essentially 100% in solution. And when we draw a reaction showing the ionization of a strong acid or base, we use a single-ended arrow showing that we go completely towards products. Anything that's not on these lists, so for instance, ammonia is not on the strong base list. So if we were showing the ionization of ammonia in water, we would use a double-ended arrow indicating that the ionization is less than 100%. Okay, so when we write these ionization reactions, one thing I notice is kind of the formulas. So the first formula here, potassium hydroxide, I see it ends in hydroxide, so I know that I can get hydroxide ion out of that right away, so I'm pretty sure that's a base. I've got hydrogen leading the formulas of the next two compounds, and when that happens, I've observed that that usually is going to be an acid. The last one here doesn't start with H, doesn't end with OH. So I have to think about what could happen. So it definitely can't donate a hydrogen, and if I have to choose whether it's going to behave like an acid or a base, I guess it could possibly accept a hydrogen. It's got a negative charge. A positive charge would be attracted to that, so that would seem like a logical way to proceed with that. So let's kind of go through and label these. This first one is what we would call a strong Arrhenius base, meaning that I can show the production of hydroxide ions by direct ionization. The HBr here, it's on my strong list, so I know that it's a strong acid. HCN is not on the strong acid. Cyanic acid isn't listed on the strongs, so it must be a weak acid, so I'm going to have to use a double-ended arrow when I show the ionization there. And then nitrite ion here is definitely not on the list of strong bases, so I'm going to go weak on that one as well. So the first thing I do usually is, if it isn't an Arrhenius base, then I'm going to write water next to it, because I know that water is either going to accept a hydrogen from a strong acid or weak acid, or it's going to donate a hydrogen to a base. So let's take care of the first one. I said that was an Arrhenius base, and we don't even need water to explain its ionization. We just get aqueous hydroxide ion by it directly falling apart into potassium and hydroxide ions. The strong acid, hydrobromic acid, we get hydronium and bromide, so the acid donates a hydrogen to the water to form hydronium, an equivalent amount of bromide. The HCN, the hydrocyanic acid, is going to be a weak acid, so I draw a double-ended arrow, and it still ionizes in the same way. So we're going to form some hydronium ion and some cyanide ion. We just won't form a quantitative amount. So if I put 1 mole of cyanic acid into water, I'm not going to get 1 mole of hydronium or cyanide out of this. I'm going to get much less once I reach my equilibrium. Okay, and then I've got water donating a hydrogen to my nitrite ion. And since water has donated that hydrogen, what's left over is just hydroxide ion. So if it forms hydronium ion by ionization, it's an acid. If it forms hydroxide ion by ionization, then it's a... Okay, one other thing that we worry about is something called conjugate pairs. And if we're dealing with a strong Arrhenius base, we really don't need to consider conjugate pairs so much in terms of the ionization. But for all other substances, we would need to consider what is going on with the ions that are formed in ionization. Okay, so one thing I always tell students is that conjugate pairs differ from one another in their formulas just by 1 hydrogen. So I've got HBr as my acid here, the hydrobromic acid. The only thing that differs by 1 H is bromide ion on the product side. So those two things are going to be connected to each other. And then water and hydronium, they only differ by 1 H. So I'm going to put those together. And then what I do is I kind of talk myself through each of this. The HBr, I know that's an acid. It's giving up its H. Things that give up H are going to be acids. So that's my acid. Water, on the other hand, if hydrobromic acid is donating a hydrogen, water is the thing that's receiving it. So that means if it's accepting a hydrogen ion, then it's a base. Then we work from the other side. Anything that's an acid, the conjugate at the other end is going to be the conjugate base. If we imagine that reaction going the opposite direction, in order to get back to my reactants, it would have to accept a hydrogen from hydronium. So that would mean it's behaving like a base. And then if hydronium is giving up a hydrogen, that means it's behaving like an acid. So it would be the conjugate acid. Okay. And as you notice, I had some Ca and Cb, because sometimes I get tired of writing conjugate. Okay, so let's connect things up here. Those two things look like each other more or less. Water and hydronium look like each other more or less. And let's see, that first thing has an H to start out with, so that must be my acid. Water has to be a base. That would mean that cyanide would be my conjugate base, or Cb, and then my hydronium would be my conjugate acid in this ionization equilibrium. Okay, nitrite here. So let's see, it looks like HNO2, and then water and hydroxide look most like one another. So let's see, nitrite, it doesn't have an H to give, so that must mean it's accepting an H. That means it's behaving like a base. And that would mean that if it's accepting a hydrogen, that means that water was donating the hydrogen. So it's behaving like an acid. So the opposites are at the other ends of those lines. So HNO2, nitrous acid would be my conjugate acid. And then hydroxide would be the conjugate base of that acid, of the water. And that's it.